Hello, welcome to a very new chapter. We are going to start talking about the concept of electrons, but in order to do so, we need to understand light and how that relates to electrons. And so there's a lot more that goes on than just the idea of a subatomic particle known as electrons. So we are going to talk about some details of light in this chapter and then move on. I can tell you that this video will probably be a little bit longer, and there is a lot of information in this video. We will go over all of this information. It'll take us probably a couple of weeks to just break down this video and to understand all of the components in regards to light. Light is a very, very complex subject, and we are just really looking at the surface of it. What you should know by the time we're done with this video is you should be able to describe the relationships between speed, wavelength, and frequency of light, understand the photoelectric effect and how it is related to the wave-particle duality of light, describe how changes in electron energies lead to atomic emission spectra, and then finally describe the Bohr model of the atom. So that's probably the only thing you recognize right now is the Bohr model of the atom, also known as the planetary model. Okay, so like I said, we're going to start talking about light and how it's related to atoms, because really we're just spending our time talking about atoms and how they perform so that we can understand the atomic structure and understand why elements perform the way they do in specific reactions. So let's do a little bit of a background. Remember, the last person we talked about when we were talking about atomic models was Rutherford. And Rutherford's model, unfortunately, did not explain why I don't even know what I was trying to say there. Doesn't explain electrons' behavior. So brief reminder, remember Rutherford, he discovered the nucleus with the gold foil experiment. But like I said, this doesn't explain why the electrons that were circling the nucleus didn't come and simply attract the nucleus or kind of collide into the nucleus. Because remember, your protons are located in your nucleus. So what is going on around? There's obviously something that's going on that's keeping the electrons away from the nucleus. So there were tons of experiments done, and really what it came down to was the study of light and its behavior, and this attributed to the idea or the concepts of matter, energy, and the atomic structure. So we need to understand the backgrounds of light before we can understand exactly why electrons do what they do. So again, Rutherford had no idea what electrons were truly doing and why they couldn't collide with the nucleus. So the first thing I want you to know about light is that light is known as dual nature, and I'm going to write that down. So that's something you should write down. Dual nature, meaning that it can act in more than one way. So if I'm telling you to write this down and I'm telling you the meaning, it's probably pretty important. So those of you that do not listen to the video, that really sucks, because I may purposely not say it in class and then put it on a quiz. And if you're not listening to this, oh, that really stinks. All right, so like I said, light can act as both a wave and a particle, known as dual nature or dual neutrality. Like I said, that acts in two different ways. So we're going to look at the first part of how light acts, and this is the wave and how light acts like a wave. And a lot of experiments have led to the idea that light is just a wave and it's nothing more. But thanks to a lot of very smart people, we know that light can act in two different ways. And so let's talk about the wave model. And so you need to know a couple things about the wave and the properties of a wave in order to understand how light works. So visible light is one type of electromagnetic radiation, which is a form of energy that exhibits wave-like behavior as it moves through space. The only type of electromagnetic radiation that we can see is visible light, which makes sense. If it's visible, it's the only type we can see. There are tons of electromagnetic waves around us at all times, and some are dangerous and some are not so dangerous. In order to visibly represent all of the electromagnetic radiation waves that are around, scientists have come up with a nice little spectrum that shows the waves in their specified order. And I will give you a copy of this and I'll show you what this looks like in class. So don't worry, I don't expect you to know this yet. You will probably know the order by the time we're done on a couple days. So electromagnetic spectrum is a spectrum to exhibit or to show all forms of electromagnetic radiation. These are not in order, but these are different types. You have gamma, X-ray, UV, infrared, microwaves, radio, and visible light. Definitely feel like I'm forgetting one, but I don't think so. And like I said, this is a spectrum or a model of the representation of all of the types of radiation out there. Each types of radiation has a different wavelength and a different frequency. And depending on what type you are, you will either have a very small or short, wavelength and a very high frequency. Gamma rays have very short wavelengths, very high frequencies, making them the most dangerous type of radiation in comparison to your radio waves that have really long waves, low frequency, not as much energy. So when you are exposed to these types of waves, you are not in any type of danger. And we use all of these types of waves or radiations every single day. Remember, radio waves, great communication. Microwaves, also a form of communication and also a great way to heat up your food. Visible light, a very, very short wavelength, but it's the spectrum that we can actually see. And then we use X-rays and ultraviolet and infrared to do not daily, but for various amounts of reasons. So within the medical field, within security, and we use all of these types of radiation. So how does this relate to light? Remember, light, we can only see visible things because of light. So that's how we're directly relating this. The visible light, or whenever I say the visible spectrum, I'm talking about light, always. And light moves at a constant speed of 3.00 times 10 to the 8th. So a few more details about waves, and in order to keep this video short, I am just going to give you very definitional terms and talk about them a few, but I am not going to draw the wave, and I will do all of that in class. We will practice all the practices of waves in class. So waves are characterized by their repetitive motions. So you've probably seen a wave. It looks, I said I wasn't going to draw anything, but I am just going to draw. It looks something like this. Those are different wave-like structures. Your short wavelengths have high frequency, and your long wavelengths have low frequency. Those are things you should know and put to your memory now. Wavelength is the distance between any two corresponding points on adjacent waves. And again, I will label everything on when we talk about all of this in class. Frequency is a number of waves that pass a certain point in a specified amount of time. This equation here relates the speed of light, wavelength, and frequency. So depending on how fast your light is moving, which we know is a constant, equals your wavelength times your frequency. And again, for the sake of time, I'm not going to label anything. I will do all of this in class. So one more concept we need to talk about, and I can tell you that this information is very strong in math. And so we are getting to a point where we're going to start talking about a lot more math and how this relates to atoms and electrons more specifically. So a really important physicist by the name of Max Planck studied the emission of light by hot objects. So if you've ever seen an object, a metal heated, it glows really, really bright, like a really red, orange colorish. What Max Planck observed was that when he was studying the emission of light with hot bodies, he found the energy of the hot body could only be lost in a small unit. So whatever energy was emitted off of these hot objects could only come off in a certain amount. And this minimum quantity of energy is known as a quantum. So quantum is the minimum quantity of energy that can either be lost or gained by an atom. So you can only gain a certain or lose a certain amount, and this is known as a quantum again. The equation that Planck comes up with is it's not known as anything, but he relates energy to frequency of a wave. So energy equals, this is the equation I'm talking about, energy equals Planck's constant times frequency. And he's so special that he even gets a special constant named after him. Planck's constant equals 6.626 times 10 to the negative 34th. And again, I know I'm going really fast, and this is all a lot of overwhelming information, but we will go over this in great detail in class. So we just spent like the last 5 minutes talking about how light can act as a wave. So a couple of reminders: the light The light is the visible spectrum of the electromagnetic spectrum. It's what we can see, and there are certain wavelengths and there are certain frequencies that we can actually see. And how light acts in a wave depends on, or so the colors that we see are determined by the wavelength and the frequency emitted. Now, light can also act like a particle. And so this is the second part of that dual nature. And this was discovered thanks to what's known as the photoelectric effect. So Albert Einstein, a super smart person, comes up with this idea of the photon. And what he does is he proposed that light could also be described as quanta of energy that behave as particles. And so it's still really a kind of a different kind of idea. But a photon is a particle of EM radiation that has zero mass and carries a single quantum of energy. Remember when we just talked about quantum of energy, it's just the amount of energy that an atom can lose. So the energy of a photon of light is quantized according to the equation that Planck came up with, which was energy equals Planck's constant times frequency. A lot of stuff that I just said there. So photoelectric effect. And so how this all relates, again, photoelectric effect is the phenomenon that occurs when light shines onto a metal surface and causes the ejection of electrons from a metal. So what happened here was that different colors of light were shown on a metal. Some of those colors bounced off and some of those colors did not. And so how they related this to energy was they said that if there was a certain amount of energy, then that ejection could happen. If there wasn't enough energy, the ejection could not happen. And so that wavelength was not bounced off of the metal. It was absorbed or it was stagnant on the metal. So red, with potentially no electrons, did not bounce off in comparison to colors like violet or blue that were shown on this metal object. Did not cause any ejection of electrons or high amounts of energy. Again, I feel like I can see the confusion on your face as I say all this, so I will go into greater detail on this. But how this relates to the atom is that here comes Bohr, another really smart person. He comes in and he's like, okay, there's something going on here. And so there's these ideas that we need to talk about before Bohr's model or the planetary models is talked about. But what is being said here is that electrons perform in different ways, and based off of the wavelength of the light that is being emitted determines how those electrons perform. Okay? So an electron and an atom tend to be arranged in such a way that the energy of the atom is as low as possible, meaning that electrons can be in a ground state. And this means that the atom is at the lowest energy state of the atom. That means that it's like hanging out. There's really nothing going on. There's no energy to make it get into an excited state. In comparison, we have an excited state. And this is potential energy is higher than that of the ground state. So the atom has become excited in some way. So something has made this atom perform in a certain way. So Bohr takes this idea of the ground state and the excited state, and he says, well, wait a minute. As an atom moves from the excited state down to the lowest energy state, it loses energy by emitting a photon of radiation. So what he says is when your atom is in an excited state, and then it goes back down to a ground state, because ground state is the neutral state of an atom, it loses some kind of photon, or it loses some kind of radiation. Some form of energy is lost. When an atom goes from a ground state to an excited state, it is being introduced or being emitted by some kind of light energy. So electrons encircle the nucleus of the atom in a specific allowable path called orbits. And so as the electron is circling the nucleus in these orbits, it can only go to different stages or different levels. And you'll also hear these levels called orbits. And so the electron can move from different energy states, and it can go up or down in orbitals. But as it gains energy, it will move up and go away from the ground state As it loses, it will go back towards the ground state, which is that neutral state. And so when the atom relaxes back to a lower energy state, it releases energy that is again equal to the difference in energy between the two orbits. Just ignore what I just said there because you're probably really confused. But what I'm trying to say is that electrons are in these orbitals, and they can never be in between an orbital. They can never be out of an orbital. They're either in the ground state, which is your first orbital, or they are moving, progressing just due to the introduction of electricity. Excuse me, not electricity, of a photon or some form of energy. I already know that there are going to be so many questions, so much information in this video. I will get to every single part of this video. We will spend probably about 2 weeks on just this information alone. So I don't expect you to know this now. I have briefly explained everything, and maybe not in the best way I possibly could. So in class, hopefully I will make this a lot more clear.